So I did like,
So now
I did the two odd induction. So I did the two, not induction. You only need induction. So I did those two odd things. I did
Yeah.
Everybody, it's about 4 o'clock here. I'm really happy to see all of you today. I hope that you're all taking care of yourselves. I'm just cleaning my hands again with this hand sanitizer. I've gotten emails from no less than 4 people in this class telling me they weren't going to be here today because they're under the weather. So that must mean it is cold and flu season. Stuff's going around, so please be careful. Get plenty of rest. Take care of yourself. Don't want anybody else getting sick. Usually what happens is about the week after the students are sick, I'm sick. So this is not boding well for me, but I'm going to do my best to keep washing my hands. I encourage you guys to do the same. Quick update here, guys. This is the end of week 4. So after today, I would encourage you to go take a look at practice quiz from week number 4. And it'll be based on the stuff from this week and just a little chance to sort of see, oh, if you're just going to give us a quiz, what might be the kind of questions that would be there. So you can take a look at that. The solutions to those practice quizzes are also in Canvas, so you can look those up as well at your leisure. Also, there is a homework assignment due on Friday. I haven't had a lot of people asking questions about it yet. If you do have questions, I'll be around tonight after this class. And also tomorrow technically is a holiday. The campus is closed. But I am going to hang in there with my Friday office hours just because I'm not really doing anything else tomorrow. And so both of my classes have homework due, and it seems like a good time to try to help people out. Also, if you ever get yourself into a situation where, you just didn't quite leave enough time to finish the problems, or you just, for whatever reason, you just sputtering through it and you just need a little extra time, you can ask me for that. I've had a few people do that. The last 2 assignments, I guess the first 2 assignments of the semester, there were a few people who didn't quite finish everything, and I don't think there was anything other than just maybe could have used a little more time. So if that's ever the case, just let me know. As long as it's reasonable, I'm sure I'll be fine with that. When we get closer to an exam, I will be a little stricter because we need to get that stuff turned in and be reviewing for the exam. But at least for right now, do the best you can, of course, to get it in on time. But I would rather have you do the problems, even if you're doing them late, than to just say, I'm just not going to turn them in and forget about it. Right. So it'd be better to just let me know, and I'll do my best to accommodate that. I did put up a couple more assignments the next 2 Fridays after this one, and that'll take us right up to the brink of our first midterm. So maybe next week I'll actually talk about the midterm a little bit. I've got a resources folder for that. I'll probably do some review sessions. Kind of outside of class, and just do some extra stuff to try to help you guys get ready for that. But we still have a couple weeks to go before we have to get too concerned about that. But it is there in the background a little bit. The first midterm, by the way, it will cover, it's right on the first of March, basically, first Tuesday of March. It's going to cover chapters 2, 3, 4, and 5. We didn't really do chapter 1. That was just kind of an intro. So everything from the beginning up through chapter 5.3, I believe. And we're currently finishing chapter 4 today. So we'll be starting chapter 5, and that'll be the last of the new material for the midterm that is around the corner. All right, so that's just kind of a little orientation on where we're at. Maybe I'll also give you an orientation on where we've been. In our class this is a pretty good summary, actually, of where we kind of were talking about on Tuesday. There were 2 main sort of parts to our class on Tuesday. The first half of the class, I was just talking about solving linear congruences. And in the second half of the class, I was talking about the Chinese remainder theorem. And I put the highlights of both kind of on this 2-column format here. So the linear congruence, right, AX congruent to B mod n, right, may or may not have a solution. And the key to whether there's a solution or not is to look at the greatest common divisor of A and N and see if it divides B. And if it does, then you can actually take the congruence and divide everything through by that greatest common divisor. And in so doing, it's actually okay to just assume from the very beginning that your system is such that the GCD of A and N is 1. Because if it's not 1, you can divide everything through by whatever it is and reduce the modulus down to N over D, basically. So anyway, so we can just assume that. We use our really handy result about greatest common divisor. It can be written as an integer combination of the two original numbers. That was one of the very first results we saw right back in January. Right, so there exists integers r and s such that ar plus ns equals 1. We just have to find those integers. That's the Euclidean algorithm, forward and backward, that goes into that. But once you've done that, you're basically home free. You just need to scale it up by a factor of b. And then your solution is just this RB part right here. Because when you take this equation and reduce it in mod n, you get A times RB is congruent to B in mod n. And so the RB is actually your unique solution. And it would be a unique solution assuming that you've reduced the greatest common divisor down to 1. Okay, does that make sense? It's probably the cleanest way to do it, making the numbers as small as possible as you go along. You don't technically have to arrange for the GCD of A and N to be equal to 1, but it does keep the numbers smaller, and it sort of gives you a simpler way of expressing your solution as well. So I kind of like doing that. Any questions so far on that part? So that's just for linear congruences. Related to this is the Chinese remainder theorem. This is a little bit different though, because now you actually have a system of congruences. We do need to assume that the moduli of these congruences that are in the system, that those moduli are pairwise relatively prime, right? So there can't be any common factors among any of those. But as long as that's true, then this system, which I labeled with a star on Tuesday, this system will have a unique solution modulo the product of all of the individual moduli. So the N1 through NR becomes your new modulus, and there will be a unique solution to your system in that modulus. Okay, so the proof of this actually constructs the solution. And so we did that last time. The solution is this kind of long-winded summation, A1, N1, Y1 plus A2, N2, Y2, and one for each subscript from 1 to R. This, as I said, is a unique solution modulo the product of the mods. Sorry, I ran out of room here a little bit. And the only thing you just need to remember from the proof is how these notations are defined. So the big N's and the little y's are actually sort of inverses of each other in the corresponding modulus, right? And so you can always solve, because these ni's are relatively prime, you can always solve this linear congruence for y sub k. Yeah, so that's kind of how that goes. So it builds off nicely from the discussion of linear congruences. So these are just two types of congruences. One is a system and one is just a single linear congruence. Two types of congruences that anybody in a number theory class ought to have a handle on, whether you can solve them or not, and if so, how do you do it, right? That's basically what I've been trying here to give you the summary of. Are there questions so far? This is just my usual 5-minute-ish recap of where we left off. The natural thing to wonder then, well, can you kind of merge these together? Can you have situations where you have a system of congruences, but they involve these types of equations rather than just X being congruent to something? And that's a variation that I wanted to say something about. So let's start off today. I'll just call this variations of the Chinese remainder theorem. And by the way, we're going to do some group work in a little bit. I'll let you practice this with some partners. But before we do the group work, I usually like to start off with at least a little bit of new material here first. So variations of the Chinese remainder theorem. I will go ahead and abbreviate that CRT. So this is a pretty common abbreviation here for the Chinese remainder theorem. And so I've got a couple of them here that I want to do with you. So the first variation, as I said, is let's suppose we have a system, but the congruences from the system actually look like the linear congruences over there on the left side. So I'll ask it as a question. So what if the system of congruences, okay, because that's what we're talking about with the Chinese remainder theorem. What if the system of congruences contains congruences of the form I'll say A times X congruent to, let's just say A sub I modulo N sub I. So I'm trying to preserve, trying to pretty much use the same notation as we had in the Chinese remainder theorem. So the A sub i's and the N sub i's, but now there happens to be some coefficient in front of the X, all right? So this is a question. So of the variations we're going to discuss, this is going to be the easier one to deal with because basically we're just going to solve this congruence first using what's on the left side. And then we're going to replace it in the system with something that looks like what's on the right side. I think I'll do an example to show that. Did you have a question? Oh. Well, yeah, it's technically the inverse of A and modulo N sub I to solve for X. But in other words, it's really just doing this. Yeah, exactly. So yeah, that let me answer this question. Like I said, this is not terribly creative. It's more or less just take this congruence, or there might be more than one of them. But for each one that you have, just apply what's on the left side over there, and then just replace it into your system. So let's just say before using the Chinese remainder theorem, replace such congruences with a new with new congruences, with new congruences of the form. New congruences of the form, and now it's going to be X congruent to, it'll be something like a B sub I, right? A B sub I, and then this would still be modulo N sub I. So you would just do that for each one. And I should add to this the words if possible. Meaning, as you know, when I say if possible, remember guys, not every linear congruence can be solved. If any one of the congruences in your system cannot be solved, then of course you're not going to be able to solve the whole system. If you can't even solve one of the congruences in that system, then the entire system fails to have a solution. So yeah, so let's just do an example of this one. Like I said, this really just sort of gluing together two things that we've already learned how to do. We can kind of just treat this as a warm-up. Suppose I ask you to solve the system. And I'm going to keep this pretty simple. I'm just going to have two equations here. So X congruent, or two congruences, X congruent to 3 in mod 5, and then X congruent to, 3X congruent to 2 in mod 7. And again, this is always sort of with the proviso of if possible, right? If it's possible to do this. So we can see that this second congruence is not in the sort of the standard form where it's solved for X. So we have to ask ourselves, so the first congruence is fine. The issue with the second one is, can we solve this for X? And the answer to that depends on the greatest common divisor of A and N. So I'm reminding you back to previous theorems, right? So the GCD of the A and the N, which in this case is 1, needs to divide this number, right? So as long as it divides B, we're good to go. So this is true. So we're going to be able to solve this one. And then what we're going to do is replace the second one in this position of the system, and then we'll solve the system. And the system will be solvable as well because these moduli are relatively prime to each other. So it should all work. We should have a solution here if we just persist with it. So let's just do it. I'm going to make this pretty fast because I made the system really nice. So if we just look at 3x congruent to 2 modulo 7, the first job is to replace it with a new congruence of the form x congruent to something. And this one, you can kind of just wing it because the modulus is pretty small. And you're really just trying to get rid of this 3 in the system. So can anybody tell me, just eyeballing it, what would be a value of x that would be the solution? 3, right? It's just 3. So if x is congruent to 3, then 3 times 3 is congruent to 2 in mod 7. So x should be congruent, x should be congruent to 3 mod 7. So I'm sidestepping this part of the work here. Is that okay with everybody? I mean, I could go back and do it. We could say, oh, let's figure out how to write 1 in terms of 3 and 7. We'll get our R and S values, and then from there we'll scale it up by a factor of 2 and write down what RB is. But whatever it is, it will be congruent to 3 in mod 7. Look okay? All right, fantastic. So now our new system, so we obtain the new system, which has the first congruence, which is x congruent to 3 mod 5. Now we have a new congruence in the second position, which is x congruent to 3 in mod 7. And I really did make this pretty easy because you're trying to solve for x as a simultaneous solution to both of these. We, of course, can go through the procedure of the capital N's and the little y's and so on. But in this case, we can also just guess the solution by looking straight at it, right? What is the x that's going to make both of these true? 3, right? Because 3 is congruent to 3 in any modulus. So I can already see the solution is x congruent to 3, and that is a unique solution. The uniqueness part of the Chinese remainder theorem is critical, by the way. It's a very important part of the theorem. It's unique modulo the product of the mods, in this case 5 times 7, which is 35. Okay, so you can very quickly come up with the solution to your system in this manner. That makes sense? It's you're just putting the two parts together. You have a linear congruence to solve first, kind of took all the fun out of that. Then you have a new linear system to solve, and I kind of took the fun out of all that too, and made it really, really compressed. But my point here was really to highlight the two parts of synthesizing the left and the right of this recap over here. So, okay, well, that's the easier variation to talk about. So a situation where within your system of congruences, you have a coefficient of the x in one or more of them. So the first job is just to get rid of that coefficient in each of them and create a system that is of this type that you can then proceed with the Chinese remainder theorem. If we're good with that, then I want to go on to the slightly more challenging one, which is what if the moduli of your Chinese remainder theorem setup are not pairwise relatively prime? Okay, that's where things get a little bit haywire. So I'm going to call this one number 2. So the second variation, right, that we can sometimes have to face would be something maybe like this. So what if, let me ask it as a question again. What if the moduli are not pairwise relatively prime? So this is variation number 2. This one will take a little bit more discussion. Okay, so if the moduli are not pairwise relatively prime. Let's start off. Question? Oh, you're going to answer it. Okay. Go ahead. I don't think I could answer it without writing a bunch of stuff down, but go ahead.
For example, x is converted to something on mod 2, and x is converted to something mod 8.
Right.
Of the highest common prime, so it would be 2 to the power of 3.
That is true. That is true. Okay. But it isn't always going to be that one mod divides the other one or anything like that. So it's a little bit special case, but yeah. Yeah. So we would definitely need to do something like that. I would like to start by just imagining I only have 2 congruences in my system. If I had 3, the way you would approach it is you would just take the first 2 in isolation first, simplify those down, solve that pair of congruences if possible, and then take the result of that and then combine it with the third congruence. And you would just kind of do this iteratively, right? So if I had 10 congruences where there was common factors all over the place among the different mods, right? You would just kind of take them, you start from the top and take the first two and simplify those down into one congruence. And then now you've reduced your entire system by one congruence. Then just do it again, and then do it again, and do it again. You can do this over and over again in that manner. You can see it would take a while. But if you had a system of 10 congruences, I don't know, you probably want to use a computer anyway at that point to solve it. So yeah, so let's consider, so I guess for the answer here, I'm just going to start off by saying for two congruences. So we'll just try to give an answer in this case alone to begin, right? So your system, which is what I've been calling star, might look something like this. X is congruent to A modulo N. I'm gonna switch letters here and just use M and N. So X is congruent to A in mod N, and X is congruent to B in mod M. And I'm trying to be consistent with the book's notation. And now I'm no longer assuming that M and N are relatively primed. And the minute I no longer assume that, I run the risk that my system won't even have a solution. I think on Tuesday gave an example of that, where if the mods are not pairwise relatively primed, your system may have no solutions. So the first thing I want to do before we even talk about how we can come up with a solution is how will we even know if there is a solution, right? So that's kind of the first thing we need to do. So I'm going to answer that first. So the system star has a solution, right? If and when we say has a solution, there has to be a modulus involved. So I'll come back to that in a second. But there would have to be a solution if and only if the greatest common divisor of N and M, right? Which we're kind of assuming now it's not equal to 1 anymore, right? It would have to divide A minus B. It would have to actually divide the difference. So that's pretty simple. That's pretty simple. You take the greatest common divisor of the mods, and it needs to divide A minus B. And then in this case, the solution is unique modulo. So the modulus in this case, does anybody have a guess what the modulus is going to be? N times M is the guess, and that would be how it works for the CRT when these mods are relatively prime. But what do you guess it's going to be in this case?
A divided by the GCD of N and M. Oh wait, no, sorry. N divided by the GCD of N and M times N divided by the GCD of N and M. So you get the parts that aren't.
There's a easier word for this. You're thinking of the right concept of it, but there's a simpler way to express it. Do you know what it's called?
Yeah. And then.
That's it. The least common multiple of the N and the M, which would be N times M if they were relatively prime. But in the general case, this is going to be modulo the least common multiple. I'm going to write that as LCM of N and M. So that's actually the modulus you need. Okay. So when you were using the example, Kim, earlier of congruence mod 2 and a congruence mod 8, I was thinking to myself, okay, well, the LCM of 2 and 8 is 8. And so that's why you were saying to use the larger mod. But in general, this would be the modulus that you would need to use. So far, so good? This is the answer to the question for how to handle this. Now, it doesn't explain how to come up with the solution yet. And also, we haven't really proved this yet. So I would like to do all of that. So let's actually start by kind of giving a little bit of a proof of this biconditional here. It is if and only if. So I should technically be proving this in both directions. Let me prove the forward direction here first. We're actually gonna write out the proof this time. The forward direction, so let's assume that we have a solution. So assume, I'll just call it X naught solves star. So suppose we do have a solution, and I'm even gonna give it a name, X naught. Okay, and so what this would mean is that, you know, n divides X naught minus A, and M divides X naught minus B. Okay, so just turning these congruence equations back into divisibility equations again. And so in this case, the GCD of N and M. Okay, so guys, the greatest common divisor of N and N, it does divide N, and it does divide M, each of which divides something else. I'm going to use the transitivity of divisibility, the transitivity of divisibility at this moment. So this guy will divide X naught minus A, and the GCD of N and M will also divide X naught minus B. Okay, so I can just turn it into a statement about what the greatest common divisor of N and M divides. And I bet you know how I'm going to finish my proof now. What am I proving? I'm working on the forward direction of this right here. I would like to know that the greatest common divisor of N and M will divide A minus B. You think we can get there with what we know on the board already? Oh yeah, for sure. If it divides X naught minus A, and it also divides X naught minus B, then it divides any combination of those two things. And in particular, I can subtract them, right? I can subtract them. So by subtraction, I love this stuff. The GCD of N and M would divide A minus B, which is the forwards portion of this proof here. Okay, so that's good. We've got that much of it done. That's the forward part. But we're going to have to go backwards as well because it is a biconditional. It's supposed to be true in both directions. Let me know if I'm going too fast, though. Far so good? And don't be shy. We're all friends here. We're all working on doing the best we can to learn number theory. So I'm sure if you have a question, people would welcome that because there's probably other questions. Yeah. Okay. Haven't talked about how to get the solution yet. We're just saying if there is a solution, we can be sure that the greatest common divisor of N and M would have to divide A minus B. Right. Okay. So that's part of what needs to be proven. And now I'm going to work on trying to convince you the other way around that this is still going to work. So let's let D. I'm going to try to convince you that there is a solution, assuming that the greatest common divisor of N and M divides A minus B. So let's just give that notation D, and let's assume that D divides that difference, right? So that's kind of our assumption. Okay, and I have to prove that my system, I'm looking at this box, I'm going backwards, I have to prove that this system has a solution. What better way to convince you of that than to actually produce the solution, right? I'm going to produce the solution given these assumptions, and that's going to be, I mean, it's hard to be much more convincing than that, okay? So this is where we're at. We got the assumption that the greatest common divisor of N and M divides A minus B. So I can do a couple of things here. First of all, I can write, this does take a little bit of notation, so giving myself room here to do this. A minus B is a multiple of D, and so I'm going to call that dt. So this is for some integer t. Okay. Now, if you're doing a real problem, this t is not some abstract t. It's a t that you can literally write down because you'll know what A is, you'll know what B is, and you'll know what D is. So this t is a number you're gonna be able to just immediately write down. Okay, and then also the other thing I'm gonna do before I get too deep into it is I'm gonna write D as an integer combination of N and M, like we always do. So let's get some notation for that. Let's write D as NR plus MS. And this is going to be for some R and S also in the integer. So a fair bit of notation here as we kind of start this thing off. So then if we kind of put these two things together, we have an expression for D, and then we have another expression for A minus B. I'm going to feed the one box into the other one and make a single equation that puts it all together. So in particular, A minus B, right? A minus B is equal to D times T. Well, D times T would just be nRT plus MST. So if I multiply through by T in my equation, then that is what we have. So far, I'm just fumbling around with a couple of equations, and I've introduced a whole bunch of letters here, right? So we have 1, 2, 3, 4, 5, 6, 7 variables in this little proof right now. Seems like a lot. But the good news now is all I'm trying to prove for you is that my star has a solution, and I can now tell you what that solution is by creating it right now. I'm going to create the solution. This is going to be the X. That's going to be my solution. And here is what it is, guys. It turns out that it's simply A minus nRT. Or if you prefer, A minus nRT is the same thing as B minus MST. Either one will work. If you just kind of rearrange the terms here, you realize A minus nRT is the same thing as, oh, actually, that should be B plus MST. Sorry, B plus MST. So if I move the B to the other side and I subtract the nRT to the left side, this is what we would have. So all I have to do is check that this really is a solution. Let's plug that X into our system. So is it true that, well, if this is my X, then the question is, what is it congruent to in mod N? A, right? So then X is congruent to A mod N. And let's just see about if I did it in mod M. Now in mod M, you might be better off looking at X this way. Multiples of M become 0, we just get B. Right? So X solves star. So it's another scenario where the proof actually shows you how to get the solution. This one will take a little bit of time. This one might even deserve to go on a flashcard set if you're making those, because there are 7 different letters. There's some pluses and some minuses in different places, and you do have to kind of get all of that right. So it's maybe not quite as intuitive as you might hope. So let's try an example of this, if that's okay. All right. So that's basically the proof. Oh, the solution is unique modulo the LCM of N and N. I really should also justify that. Before we do the example, let's just make sure the uniqueness part is clear. I will do that in the same old standard way. I'm going to assume there's another solution, and I'm going to prove the 2 solutions are congruent modulo that least common multiple of M and N. Okay, so let's just make sure we don't leave that out. So the uniqueness, just really quickly here at the end of this proof. Right, so just a quick comment on the uniqueness part. Let's suppose that Y also solves star. Right, suppose that there's some other solution. We have X solving star, and now suppose that Y also solves the star. Well, what does that mean? That means that X is congruent to A, but Y is also congruent to A, modulo n. Yeah, and x is congruent to b, but y is also congruent to b modulo m. Okay, so just using the basics of what congruences are about, this tells me that n divides x minus y. So if I subtract the x from the y, n would be a multiple of that. And m is also a divisor of x minus y. So the two congruences can be written as divisibilities like that. And so this proves that x minus y is a common multiple of n and m. Let's just write that in words here. X minus y is a common multiple of n and m. And any common multiple of two numbers will itself be a multiple of the least common multiple of those two numbers, right? So if x minus y is a common multiple of n and m, then I can take the least common multiple of m and n, and I know that it would divide x minus y. Okay, so the LCM of n and m is a divisor of any other common multiple of n and m, such as x minus y. And that is basically proving that the x and the y are the same in the world of mod LCM of m and n, right? So in other words, let me just notice how I'm kind of going back and forth between congruence statements and divisibility statements. It's really just where the whole definition of modular arithmetic started from. So we're still just kind of milking that a little bit further. So now I'm going back to congruences again, and I'm just going to say that x is really the same as y, congruent to y, in other words, modulo the LCM of n and m. How do you like that? Right? That's how that works. Okay. Make sure everybody's up to par with me on that. And if there's a question, we can do that. Otherwise, what I really should be doing is an example to kind of make sure this is all good. Okay. All right. Let's do an example. Okay. Wow, this semester is going fast. I'm on page 27 of my notes already. I don't even have 100 pages. So anyway, we're moving right through it. Okay, so here's the example. I'll start this off. I'll preface this with if possible, because now we have concerns about whether this is possible or not. If possible, solve. I'll call this the star system. So I'm going to go ahead and label it with the star again. And I'm going to give you some congruences. There's going to be 3 of them this time. So x congruent to 2 in mod 4. And then x congruent to 4 in mod 6. And then x congruent to 7 in mod 9. Again, just to make this reasonable for a lecture like this, I didn't pick numbers that are too big. You might even play around in your mind with that and manage to think about what the solution would be, but that's not really what I care about. I want to understand how this process, which is really this is the part we really need to focus on, how it really works, okay? So for this solution, the first thing, I mentioned this earlier, that we were talking about having only 2 congruences. So what I'm going to do is I'm only going to take the first 2 congruences. I'm going to set the third one aside, at least for the time being, and then we'll bring it in a little bit later if necessary. So let's just consider x congruent to 2 mod 4, and at the same time x is congruent to 4 in mod 6. So I'm just going to play around with this. And what would really be helpful, the way I would recommend doing this is if you can really learn what all of the variables over here represent, let's just write down what all the variables are. For this system, you know, N is 4, M is 6, right? A is 2 and B is 4. So the A and the B from the original system here. And then we need to figure out the D. This is the first one we actually have to calculate. D is the greatest common divisor of N and M. In this case, the greatest common divisor of 4 and 6 would be 2. So that's D. Once you know what D is, you should be able to tell me what T is. Because the first box on the board over here tells me that A minus B should equal D times T. So if we do the math on that, A minus B is -2 and D is 2. So what would T be?
-1.
It's -1, exactly. So that's -1. All right, so we're getting there. The other variables that we need are the R and the S, which comes from the second box. The second box here. So I need to figure out how to write 2 as an integer combination of 4 and 6. And I bet you can do that without actually using the Euclidean algorithm. We could just write it down. So note that 2, which is our D value, is equal to 4 times something plus 6 times something, right? This is what we're trying to fill in. And the well, this is not a unique choice, as we've discussed in the past. There's not just one answer here, but I can certainly give one possible answer would be to choose a -1 and a 1. And the N goes with R, so R is -1, and the S value goes with M, which was a 1. Okay. Wow. So this is what you do. You write it all out. And then the solution, maybe I should have had a box around this also. The solution for X is either one of these two expressions. So I'll just use the first one. So X is equal to A minus nRT. So we just plug in the numbers now. 2 minus 4 times -1, and then T is also -1. And actually that comes out to 2 minus 4, which is -2. And this is a unique solution modulo the LCM of 4 and 6, which is 12, right? So X is congruent to -2 in mod 12. Okay. So far, so good. It's very computation driven here. I mean, well, this is a class on number theory, so you've got about 8 numbers you have to juggle all at the same time in this process. So we're not done yet. What we did is we collapsed the first 2 congruences into a single one here, right? So let's keep going. Okay, so now we have the first congruence that we're going to use is just X congruent to -2 mod 12. And then the second congruence is just the one that we haven't touched yet, which is X congruent to 7 in mod 9. So we've reduced ourselves down from 3 congruences to 2. I guess I'll call this star prime. Yeah, Tanner?
This is a notation note.
Sure.
So we're allowed to go from the equal part, and we're going to change that last one, the mod, or the sorry.
I should write this as a congruence here. You're absolutely right. So that should be a congruence. So if you preferred to write X as being 10 or 22 or 34 or whatever, any of those would be fine as well. Yeah, thank you. Yeah, anytime I have the word mod N on a statement, it should be with a triple bar line, not a regular equal sign. So yeah, thank you. Thank you. Okay, great. Everything else okay so far, guys? We're so good? Okay, so now we just want to solve this one, okay? And I'm going to go through the same alphabet soup of writing down all these variables one more time. So we're starting over So what's written here, those numbers are all gonna get replaced now. So now I'm gonna have n equal to 12, m equal to 9. Right? A is equal to -2, B is equal to 7. And by the way, it's perfectly reasonable. We could stop and check at any moment here. Is it really true that A minus B is a multiple of the GCD of M and N? So we should write down the D here. The GCD of M and N is 3. And if you look at A minus B, yeah, it's -9. If A minus B was not a multiple of D, it's going to be game over, right? At that point, there's no solution, you just stop. Even if you've managed to solve this one, if you can't figure out an integer for T, right? If T is not an integer, it's basically game over. Your system is not solvable. With me, right? So in this case, the D is 3. The A minus B is -9. So what is T?
-3.
It does work, it doesn't it? It is an integer, which is -3. Guys, I'm kind of using this board over here as a cheat sheet as much as you are. I mean, I wish I could tell you like this is planted in my brain, where the R goes, where the S goes, where the T goes, but it's not like just second nature. You don't feel bad if you're like peeking over at what we wrote over there. We definitely need to use that. The next thing we need to do is figure out how to write D as an integer combination of N and M. So D was 3, and it needs to be an integer combination of N and M, so that's 12 times something plus 9 times something. And I'm just going to eyeball it again, just to save a little time. If I want to eyeball this one, well, what do you think is the easiest solution? 1 and -1, right? So I'll just choose a 1 here and a -1 here. And of course, those are the R and the S values in the notation. Okay, so I think we should be able to write down what X is for us. X is going to be A minus nRT. I'll just use that one again. So that's -2 minus N was 12, R was 1, and T was -3. Just feed those values in there. That looks like -2 plus 36. -2 plus 36, which would be 34. And before I get in trouble, I'm going to make that a congruence sign. And this is going to be in modulo LCM of 12 and 9, which is 36, right? So this is mod 36. And so that would be your answer, 34. And you can check it. Does 34 work here? Does 34 work here? And does 34 work here? And it does. If you prefer, you could, of course, change 34 to -2. And that's easier to even easier to just plug those into these. In fact, if you've been really clever noticing this, even before we started this problem, we could have said, oh, that's the same as -2, that's the same as -2, that's the same as -2. And now by inspection, X is going to be congruent to -2. And it'll be modulo the LCM of all 3 of them, actually, which is 36. So you could have gotten this answer without all of this fussing around, but it isn't always possible to do it that fast. So just wanted to show you the full details on it. Okay, what do you guys think? Questions on that? This is the variation where the mods are not relatively prime to begin with. Everybody happy? Or am I the only one happy? Sometimes I think they're paying me to teach these classes just for my own entertainment. I always seem happier than the students. And it's like, well, wait a minute, you guys are the ones paying for the class. I'm just here for my own entertainment. I always say I would do this job for free. Sometimes I think the university is listening to me. No, I'm just kidding. Anyway, yeah, so that's another variation of the Chinese remainder theorem. Well, what other variations could we do? Maybe instead of linear congruences, we could have nonlinear congruences. So maybe instead of just, you notice every single congruence on the board always has just an x or some scalar multiple of x. We don't have an x squared anywhere. I don't see x cubed. But what about solving congruences? There, we could make a whole big polynomial for that matter, right? Just create some, just take your favorite polynomial that you know from high school. And, you know, instead of equals 0, write congruent to 0, modulo, and then pick a modulus that's fun to play with. And then see if you can solve for x. Oh, so many things that you learned in your high school algebra courses will no longer work. I'll just give you one example. You all know, I think you all know that a polynomial of degree n can have at most n solutions. Even if you count repeats and even if you count complex numbers, you would never have more than n solutions. So that's pretty well known. Turns out, not true in congruence world. I can take just a quadratic congruence and find tons of solutions to it if I pick my modulus right and I pick my number right. So there's a lot of weird, wacky stuff that goes on as soon as you just, all you got to do is take your polynomial and change your equal sign into a congruence sign and pick a modulus. And depending on what modulus you pick, it could be a very interesting conclusion. So we have a long way to go to talk about a lot of this stuff. The first step really to addressing nonlinear congruences is just going to be dealing with powers of integers in a modulus. And there is some famous result on this. It's called Fermat's Little theorem. I know a few people who've even asked me already if they could use it on the homework. So I know some people are aware of Fermat's Little theorem, not to be confused with his last theorem, which is an even more challenging result. But that's where we're going to go next. And that's really in chapter 5. This is kind of, you know, take a breath. This is kind of a good place to sort of pause and reflect. This is the kind of the end of chapter 4. Does anybody have any questions so far? Yeah, please.
This example we just did,
Okay.
we have solved the first and the third congruences since they're pairwise prime, and then
Yeah, that's a really good point. So if we had wanted to, there's nothing that says you have to go down the line in order. So you could work on the first and third one and just use the regular Chinese remainder theorem there. And that would collapse to a single congruence in mod 36. And then you could combine that with the other one, kind of using the technique you just went over. Yeah, that's a good point. So yeah, I don't mean to suggest, I don't want to suggest to anyone that there's really only one way to do these problems. Okay. Make sure that you are doing more than just eyeballing solutions. Like I know sometimes you can like, oh, I could just see that -2 is a solution and turn it in, right? But you do need to practice kind of the process that generally works, because you never know when it's usually at bad timing, like on the exam, when suddenly your brain doesn't work and it's like, oh, I can't just eyeball this one and I need to go through it. So make sure you know how the procedure works. Even if maybe on some of the examples, you could just shortcut it and just write down the answer. So actually, as I said, this is kind of a nice little break between chapters, so to speak. I think this is a good time to have you guys practice a little bit. I brought a couple of linear congruences along with a Chinese remainder theorem example for you guys to play with. So I am going to send this handout around to you guys, and we'll spend a little bit of time letting you guys grab partners and I guess take the reins on a little bit of this. How are we doing back here, guys? Good. So you can grab, just like you've done before, 2 or 3 other people aside. And grab 2 or 3 other people and let's come on up to the boards. I'll let you guys work on group work number 4 together.